Good evening, everyone. Welcome to Sapience Education. Myself, Gautam Sharma. I welcome you all in the Sapience Education. So today I am going to discuss about the first part of the electromagnetic induction. What is electromagnetic induction? Let us see here the phenomena. The phenomena of generation of current or EMF by changing the magnetic field is known as electromagnetic induction. First thing we can consider or understand that how electricity can be generated. Okay, how electricity is being generated. The basic principle is that it is an electromagnetic induction. So let us consider there is a circuit like this, and I want to produce a current in the circuit. So what should I do? So I don't have any power source, so we need to put a magnet. So if you put a magnet like the north south poles and a magnetic field is passing like this, so what happen if you move fro and to and fro movement, so what will happen? You will get a current. Okay, you will get the current. The EMF developed in the conductor by the process of EMI is known as induced EMF. Whenever EMF is developed by the process of induction, so these are the method of induction. So by the induction only we can produce a EMF. Okay, then the current flowing through the conductor is known as induced current, and it is reverse process of magnetic field production by electric current. See, let us understand basic thing is that there is a there is a current carrying conductor. There is a current carrying conductor. Okay, so let us consider there is a current carrying conductor. So what will happen? It will create a magnetic field. Okay. So if current is being produced, so it will create a magnetic field. But if you just think that if the magnetic field is there, uh, just you reverse it. So if you change the magnetic field like north pole and south pole, so what will happen? It will create a current. So this phenomena is known as electromagnetic induction. So this is very important phenomena by which we can understand that we are getting a AC current or any DC current. So earlier it was only power source like chemical energy to electrical energy, but now AC current has been developed by just mechanical energy to a electrical energy. Okay. So it is the reverse process of magnetic field production by electric current. The phenomena of EMI was discovered. So see, again I'm telling you that if there is a coil and I want the current to flow through this coil without any power source, so what should I do? Just I should move, I should move any north pole and south pole magnet like this to and fro. So when you move to and fro, so what will happen? It will create a, it will create induced current, or induced EMF, we can say that. Okay, so this is the phenomena of production of electromagnetic induction. So we will study details more. Now what happens? See here how to create a current. Before that, we need to understand basic things. The total number of magnetic field lines crossing through the surface normally when it is placed in a magnetic field is known as magnetic flux through that surface. So this is, see here, this is our surface. Okay, and if a magnetic field lines is passing through this, so 1 2 3 4, so these are the flux. Flux can be considered as number of field lines per unit area. Number of field lines per unit area. Okay, so this is considered as flux. So the total number of field lines line crossing through the surface normally when it is placed in a magnetic field is known as magnetic flux of that surface. Okay, it should be placed normally. If it makes an angle, so what will happen? It will reduce. See, if you place this area, suppose 1 2 3 1 2 3 4 5 6 6 lines are now passing. Now let us make this plate tilt like this. So what will happen? So just I made a plate like this, tilt like this. So what will happen? So number of field lines passing has been reduced. One, 2, 3, 4, 5. So maximum number of lines which is passing through is when the area vector is parallel to the field, or surface is perpendicular to the magnetic field. Okay. Now see here, we will always compare everything with the area vector. Area vector means, let us consider this is a surface. So at this surface, the area vector will be always perpendicular. So here we can consider this is a surface area and the area vector is this n cap. So how much angle is being made by the area vector? So this is theta is equal to 0, right? So when theta is equal to 0, so the flux will be maximum. Flux will be maximum. So flux will be, can be written as B dot A. So we can also call that BA cos theta. When theta is equal to 0, that is theta is the angle between, theta is angle between area vector and magnetic field. So theta is the angle between area vector and magnetic field. So finally we can put here theta is equal to 0. So phi will become is equal to BA. Phi is equal to BA. Okay. So this is how we have understood what is the flux. Now see, these are the number of field lines passing through this and it is changing. So it is known as flux. It is known as flux. Okay. I hope you have understood this. Now suppose a loop in area A is placed in a uniform magnetic field B, then the magnetic flux through the loop is given by integration of B dot dA. So any loop, let us consider any loop, and this is an angle theta and it is making an angle theta. So when a magnetic field is perpendicular to the plane of the loop, so the magnetic flux will be given as BA. Okay. Magnetic field is perpendicular to the plane of the loop. So you should always try to remember this. So let us consider this is a loop and magnetic field is perpendicular. When magnetic field is perpendicular, so the flux will be equal to BA cos theta. So area and theta is the angle between area vector and magnetic field. So theta is here equal to 0. So flux will be maximum. Okay. And if it change, if the angle between magnetic field and area vector is somehow greater than 0, so flux will get reduced, right? So the basic definition for finding a flux, that is equal to phi in anywhere. If you want, so the best formula to use is B dot dA. Now according to situation, just you use it so that you will able to get the proper result, right? Now see here, see, you can see the scenario. This is the case when area vector and magnetic field both are making an angle theta is equal to 0. Here theta is equal to 90 degree and here theta is equal to some non-zero degree. Okay. So here flux will be equal to 0. So what you have learned, that whenever any surface is parallel to the field, so flux will be 0, right? Flux will be 0. Got it? And any plane perpendicular to the magnetic field, then the flux will be maximum. And if there it is in at an angle of theta, so it will create an flux which is between 0 to maximum. So I hope you have understood this. Now the SI unit of the magnetic flux is Tesla meter square or Weber. So flux, again you just remember this, SI unit of flux is flux SI unit is equal to WB Weber. 1 Weber is equal to 1 WB, that is equal to 1 Tesla meter square. Okay. Now, how you will define 1 Weber? 1 Weber is the amount of magnetic flux over an area of 1 meter square held normal to the uniform magnetic field of 1 Tesla. Amount of magnetic flux over an area of 1 meter square. Let us consider this is an area having a 1 meter square, and there is a uniform magnetic field. So, magnetic field. So, what is the value of this magnetic field? Is B is equal to 1 Tesla. So the flux will be equal to BA cos theta. So here theta is equal to 0. So B is equal to 1. So 1 area is equal to 1. Cos 0 is equal to 1. So finally, flux, the amount of flux is known as 1 Weber when magnetic field is 1 Tesla, area is equal to 1 and held perpendicular. So the amount of this is known as 1 Weber, and 1 Weber is equal to 10 to the power 8 Maxwell. 10 to the power 8 Maxwell. Okay. You can also called as a flux as a unit of Tesla per meter square. So you can use this also. Now see here, experiment done by Faraday. Experiment done by Faraday. So from here you can understand that this is a magnet. Okay. What happen when it moves away toward it? So what will happen? Flux will change. And if flux will change, if phi will change, what will happen? It will create a induced EMF. Induced EMF. And this induced EMF due to which bulb lights, right? So this is what experiment has been done by Faraday and Henry. Now first experiment is conducted, and in this experiment what happens? There is a circuit. There is a circuit like this. There is a circuit like this. Okay, so these are the circuit, and now this is your magnet. So it is held stationary. So if it is at rest, so current is 0. But when it moves, so current is non-zero. Current is either 1 ampere, 2 ampere, 3 ampere. It means that if you want to create a current, so you need the movement of the magnetic field. Movement of magnet or change in a flux. So earlier flux was there like this, but when you move ahead, forward, backward, so change in flux will happen. Change in flux will happen. Okay. Now this is your second experiment. A second experiment, EMI with the one coil is stationary, another coil is moving. See here, as we know that this is a coil. This is a coil, and it is coil, and it is creating a magnetic field like this, right? Magnetic field like this. Now what happened? It is power source. It is given as a power source. So due to which it will create a magnetic field. So magnetic field will also get linked with the another coil, and when you move this coil, so it has been seen that there is a generation of a electric current in this coil, that is EMF is being created. So this is also second experiment done by the Faraday. Third experiment. Third experiment, what have done? This is the power source. What happens? It has closed switch on and off. What happens when you switch on? So current will suddenly increase, and after that it will become constant. So when in the period when the current increases, so what happens? Magnetic field will change because current is changing. So if current is changing, so magnetic flux will change. So what it has been seen that EMF is generated. EMF is generated, right? Now, if again, when it is being switched on for a long period, so current become constant. See here, current starts increasing and become constant. But when current is constant, so it has been seen that the reading is zero. Why? Because no change in a flux happen. Magnetic field is there, but no change in a flux will happen because field number of field lines is not changing with the area. So that's why what happened? There is a no current is produced in this. What conclusion we can draw? We can draw the conclusion that current can only be produced when there is a change in a flux. So this is the third experiment done by the this. Okay. Now we will discuss about the Faraday's law of electromagnetic induction. So this is Faraday's first law of induction. Whenever the amount of magnetic flux linked with the circuit changes, an EMF is induced. And the SI unit of this induced EMF is voltage, and the actual number of magnetic field lines passing through the circuit does not depend on the value of induced EMF. Induced current is determined by the rate at which the magnetic flux is changing. So very important. See, let us suppose this is a circuit. You have kept a weak magnet, and and if you replace this weak magnet with the strong magnet, so what will happen? You just keep no current will be induced. Current will be only generated when there is a change in the number of field lines. That is flux change, rate of flux change, rate of change of flux happens. If rate of change of flux happens, then only current will be introduced. This is the Faraday's first law. So it means that Faraday's first law, as per Faraday's first law, EMF is proportional to the rate of change of flux. It is not equal to proportional to d phi. It is rate of change of a flux. Whenever there will be a change, then only EMF will be induced. This is the final one. So the Faraday's second law, the magnitude of the induced EMF in the circuit is equal to the rate of change of magnetic flux through the circuit. Mathematically, Faraday's second law can be expressed as this. EMF is equal to minus d phi by dt, where d phi can be written as change in flux, that is equal to phi 2 minus phi 1, and time dt is equal to written as t2 minus t1. Now, there is a negative sign. You have seen that there is a negative sign. Why there is a negative sign has been used? The negative signs in the above relation indicates that the induced EMF in the loop due to change in a flux always oppose the change in a magnetic flux. Let us suppose, see, try to understand. This is your circuit. And there is a magnet. There is a magnet like this. Okay. This is your north and this is your south pole. Okay. Now what happens? If you move this, so current will be induced in the circuit, right? Now the thing is that in which direction current will be formed. Now see here, current will be formed in such a direction that it will oppose the cause. This motion is caused, for example, north pole is coming, so it will create a current in such a way that it will also create a north pole. That means it will create an anti-clockwise rotation. If it will create a north pole, then what will happen? It will try to push it. So induced EMF is such that it will be always negative to the applied. Okay. So that's why EMF is equal to E is equal to minus d phi b by dt. If there is n number of turns, so this for one turns it is your EMF is equal to minus d phi by dt. but for n turns, like 1, 2, 3, 4, 5, 6, 7, n turns. So for n turns, the EMF can be written like this. So induced EMF can be increased by increasing number of turns of a closed coil. So if you increase the number of turns in a closed coil, so what will happen? EMF will be increased. Okay. So I hope you have understood. Now, induced EMF and a current. If N is the number of turns and R is the resistance of the coil, and the magnetic flux linked with its turns changes by d phi in a short interval of time dt. So induced EMFs can be written as E is equal to minus N d phi by dt. Now, what about the current? So, current is equal to potential difference by resistance. Now, E by R. So, what is the value of E? Minus N d phi by dt, but divided by R. So, finally, we have got current I as just like this. Now, electric charge. So, Q is equal to I into T. So, I dt. So, from here, we can just get this. So, I hope you have understood this. So, these are the formula, very important formula where you can use this and find the solution. Okay. So, I hope it is enough for this part. So, I will meet in next second part so that I can more elaborate more, lots of things. Thank you.